Okay, guys, I'll get started with the lecture. In fact, before I do, I'll just draw your attention to the fact that I've written down some references to the Stewart textbook. So this is the 7th edition of the book entitled Calculus by Stewart, which is the textbook for this course. I've just had a few questions about some of the material, even the background material that I talked about in the first lecture. And I just wanted to point out that in Stewart, the topic of ODEs are covered in a couple of chapters. In chapter 9 is an introduction to first-order differential equations, and in that chapter, amongst other things, the two classes that I talked about in my first lecture, which were the separable differential equations and the linear first-order ones. And what we're going to talk about today are second-order linear differential equations, and in particular, we're going to look at a method for solving these so-called non-homogeneous linear second-order ODEs. And this method is often called a method of undetermined coefficients. Right? So I'll be talking a little bit about some of the background material. So I guess I could say plus some revision is covered in this chapter. But I'll show you this method of undetermined coefficients. Some of you may have seen it before. I assume most of you have done Math 1052, and so in some cases you would probably be able to solve equations of this form with a certain type of function on the right-hand side here. Okay, so that's really what we're going to be looking at, is solving equations of this form. All right, so it's a second-order equation. Remember what the order of a differential equation means. That's the order of the the highest order of the derivative of the unknown function that appears in the equation. So in this case, the second-order derivative is the highest order derivative that occurs in the equation, so it's a second-order equation. And it's a linear equation. We can identify this as a linear equation because the unknown function y and all of its derivatives appear linearly in the equation. And just, I guess this is a standard form. The way it's written on page 21 here is to write all the unknown function y and its derivatives to one side. All right, so this is a linear second-order differential equation, and it's non-homogeneous if this function r that stands alone on the right-hand side is non-zero. If it's zero, we call the equation homogeneous. All right, so I guess before I show you this method of undetermined coefficients, it's worth going over a bit of background, and really I'm looking upon this as reminding you about some of these results. Okay, and actually what we cover in today's lecture will be relevant for two of the assignment questions on assignment 1, questions 2 and 3 in particular. Question 2, I think most of you would be able to do already, in fact. That's just a little bit of fun, in fact, that question. But question 3 I'll say a few words about throughout this lecture. All right, first of all, just some revision. This superposition principle is a very important principle for homogeneous linear differential equations. And, I mean, in particular, we're focusing on second-order linear equations, but a lot of the concepts that we'll meet in this chapter, a lot of the concepts generalize to higher-order linear homogeneous equations, right? So the second order is really the place where we can establish some of these results. In the first order case, some of these results that I'll be talking about are quite trivial. All right, so the superposition principle now is just for linear and homogeneous equations. So that's with that function that function on the right-hand side, this r of x, when that equals 0. Okay, so we're only talking about the homogeneous equations now. So for any homogeneous linear equation, if we have two solutions, I've called them y1 and y2 in the text here, then I can take any linear combination of those two solutions and still have a solution. That's the superposition principle. All right, so I'm not going to prove this, I'm just reminding you of some of these results. It should be familiar to you. All right, so that's this linear combination here where A and B are constants. And often throughout this lecture and subsequent lectures, I'll refer to those constants as being arbitrary, meaning they can take on any values, the result still holds. Okay, so that's the superposition principle. If I've got two solutions, I can take any linear combination of those and I still have a solution. Or I guess another way of saying it is that I can take an arbitrary linear combination and still have a solution. All right, but actually we can go one step further and talk about the general solution. And so in this case, the general solution is a form of the solution which contains all possible solutions to the problem, to the differential equation. So if we've got a homogeneous linear ordinary differential equation, so homogeneous meaning the right-hand side here is 0 when it's written in this standard form, okay? The general solution is of this form, so it's an arbitrary linear combination of these two solutions, y1 and y2, but where now we specify that these two solutions are linearly independent. Now here we're using this language of vector spaces, and actually that's no coincidence. We can use words like basis and dimension and things like that in the context of solutions of a linear homogeneous differential equation. In fact, there's no problem with using that language. In fact, what we can find, although I'm not going to talk about this in too much detail, but we can talk about the space of solutions, the vector space of solutions of a linear homogeneous differential equation. Okay, and so we can talk about a basis of solutions and so on. So in this case, talking about linearly independent solutions, because we're only dealing with second order equations, that's quite straightforward to check. That we have two linearly independent solutions. We just need to check that one function is not a multiple of the other, right? Not just a constant times the other. All right, so I guess you could think of it as check y1 divided by y2 is not a constant. All right, and then they're linearly independent. If we're dealing with higher order equations, though, it becomes a little bit more challenging to determine whether or not we have a linearly independent set of solutions. In fact, in one of the lectures next week, I'll talk a little bit about that. Okay, so anyway, in this case, whereas the superposition principle merely states if we have two solutions, take an arbitrary linear combination, we still have a solution. This result says if we have two linearly independent solutions of a second order linear equation, then we take an arbitrary linear combination of those and we have the general solution. In fact, that result generalizes to higher order. If I had a fourth order linear homogeneous differential equation and I had four linearly independent solutions to that equation, then an arbitrary linear combination of those four solutions would be the general solution, all right, with arbitrary coefficients. Okay, so we can also talk about initial value problems corresponding to these differential equations, and because it's second order, an initial value problem involves some data of the solution and its first derivative at some point. So in this case, for example, an initial value problem would consist of the differential equation and these 2 points of data. So y at some value x naught takes on this value k naught, and the derivative of the solution at x naught takes on some value k1. All right, so that's the general solution. So when we talk about solving these linear equations, we talk about trying to find the general solution. All right, so in the special case where we have a homogeneous differential equation with constant coefficients. So now we're talking about the case where these numbers a and b are constant, so that's these coefficients that appear in the equation that are the coefficients of y dashed and y. We're now just assuming they're numbers, not some functions. As I've written above at the top of page 22, we've got p of x and q of x, where I guess we should specify that p and q are some continuous functions of x. All right, so now in the special case where a and b are constants, we can actually go one step further and work out what the solutions look like. We can work out what the general solution looks like. So this is, again, a bit of revision, just going over it quickly here. But because if we look at this equation with a and b as constants, what we're really saying is we take some linear combination of a function and its first derivatives, where the coefficients are just constants. So we're looking for a function that is related to its first and second derivatives up to a constant. Then there's one such function that we know of, is the exponential function. Okay, we know if we take a function of this form, so if we take y to be equal to e to the lambda x, okay, we know if we differentiate that once, we just get a scalar multiple of y. All right, when we differentiate the exponential function, this index, this exponent lambda, comes out the front, and we end up with y dash being equal to lambda times y. Okay, so the first derivative is just a scalar multiple of the function itself, and similarly for the second derivative. So, for such an equation, if we make this assumption, substitute that into the differential equation, what we end up with is a quadratic equation in this exponent lambda. All right, this should all be familiar to you at this stage, and I'm going through it quite rapidly, I acknowledge that. All right. So, okay, we've got this quadratic equation in lambda now. So a and b, remember, are specified in the statement of the problem. They're the coefficients in our differential equation. So we have a quadratic equation, so we could use the quadratic formula and write down the form of the values of lambda that satisfy this. But we note that three things can happen. All right, the first thing that can happen is this quantity inside the square root, a squared minus 4b, could be positive. The second thing, it could be 0. And the third thing, it could be negative. All right, if it's positive, we end up with two real values of lambda. All right, so we end up with distinct, so meaning they're different, right? Real distinct values of lambda, say lambda plus and lambda minus. Okay, so since we've got two different values of lambda, remember what the result on the general solution says at the top of this page, that's just off screen, says that all we need are two linearly independent solutions in order to write down the general solution. Okay, so if we can work out two different values of lambda that satisfy that quadratic equation, often called the characteristic equation of the differential equation, then that means we have two values of lambda up here for which e to the lambda x is a solution to the equation. All right, so two distinct values of lambda means that, well, if I take the ratio of those two subsequent functions, I'm not going to get a constant, which means they're linearly independent, which then means the general solution for that case, where a squared minus 4b is positive, will just be a linear combination of those two exponential functions. Okay, but what happens if a squared minus 4b equals 0? In that case, we only end up with one value of lambda. Okay, we only end up with one root of this characteristic equation. All right, now in such a case, we can still work out a second solution. And so just relating to this second case, I'm not going to work through the calculation or work through the proof of this result, but I believe you've seen this method that's known as reduction of order. Okay, I'll just outline that method. So we have, from this calculation, we have one root of the characteristic equation, that is one value of lambda. So that means we have one solution only. Okay, so y1 is e to the alpha x. We have one solution only, but remember what the result at the top of this page says. To write down the general solution, we need two linearly independent solutions. We've only got one. So what we can do is say, well, let's set y2 equal to some function u of x that we insist is not just a constant, it must have some non-trivial dependence on x, so it must be a non-trivial function of x, in the sense that it's not just a constant, multiplied by that first solution. All right, so in this case, we know what the first solution looks like. Y1 is just e to the alpha x. Okay, and then what we can do is substitute this y2 into the ODE, and we'll end up with some equation, but now that's an equation involving u. And it turns out it will be a first-order equation in the derivative u dash. So what we could do is, say, introduce another function, set v equal to the first derivative of u, and then it will be a first-order equation in v. Right? And hence what we've done is reduce the order of the differential equation from a second-order ODE to a first-order ODE in the first derivative of u. So sub into the ODE. And then ultimately this allows us to find that function u of x. All right, and this method is known as reduction of order. All right, it turns out for this case, right, for the case where we have, so right at the top of the screen there, the case where we have second order linear homogeneous equation with constant coefficients, it's possible to show using reduction of order that this function u is only ever going to be linear in x for the second order equation. All right, so in other words, the general solution will be determined, or this second solution will be some, well, you could write it as just x times e to the alpha x, or alternatively you could leave the constants of integration throughout and still obtain this general solution. Okay, but it's reduction of order that gives us this information. In fact, and this is where I could make a comment about question 3 of assignment 3. You'll notice that question does not have constant coefficients, but actually I've given a hint in the question that says, notice that, what was it? I forget exactly what the solution was, but I've given one solution to the corresponding homogeneous equation. In question 3, actually I should have brought along the assignment question, but in question 3 of assignment 1, it's a non-homogeneous linear second order equation. Right? It's non-homogeneous, so the right-hand side is non-zero. And what I've given you is just one solution of the corresponding homogeneous equation. Right? So if you think about that, what you could do is, since you have one solution of the homogeneous equation, you could set y equal to u times that first solution that I gave in the hint, and use reduction of order to determine your general solution. It is actually possible. So you could try doing it that way. You could break it down into smaller steps if you like. Okay, so anyway, just you might like to make a note of that for assignment 1, question 3, that you could try using reduction of order. Okay, so there's a third case to consider here, right? I've only talked about the two cases, so let me just remind you what we can do with that third case. The third case for the roots of the characteristic equation is where a squared minus 4b, which I guess I could just call it the discriminant. This discriminant is negative. Okay, it's the expression that discriminates between these different cases. So this a squared minus 4b could be, if it's negative, that means the lambdas, we end up with two distinct values of lambda, but they appear as a complex conjugate pair. And after a bit of rearranging and using properties of trig functions and so on, you end up with, so using the complex form, so in this way you end up with this complex conjugate pair, say beta plus I omega, where I is the imaginary unit, so I squares to -1, then you end up with these two linearly independent solutions. One is e to the beta x times cos omega x, and the other is e to the beta x sine omega x. So you take an arbitrary linear combination of those two linearly independent solutions, and you have the general solution. All right, so again, this is revision. So I don't really want to spend too long on that. It should be reasonably familiar to you. I'm not so sure how familiar you are with this reduction of order method, but it's my understanding that most of you will have seen this before. Okay, so what we're really interested in this lecture is using this method known as the method of undetermined coefficients to solve these non-homogeneous linear second-order equations. And what it really involves is having a look at the form of that function on the right-hand side. So because we assume it's non-homogeneous, right? Remember, that means that this function that appears on the right-hand side is non-zero. Okay, we have a look at the form of the function on the right-hand side and make a good guess. Right? Make a good guess for the particular solution. So the theory is that we've just seen, relating to a homogeneous equation, we need two linearly independent solutions in order to write down the general solution. But what if we have a non-homogeneous equation? Well, it turns out, and again, this is something you should have seen from Math 1052 if you've done that course, that the general solution is always of this form. So it's always of this form YH plus YP, where YH is the solution to the corresponding homogeneous equation with R equals 0. Sometimes that's called the homogeneous solution or the complementary solution. You may have seen YH referred to as that, and this YP is referred to as a particular solution. Okay, and so it's only this YP, this particular solution, that contributes to the function to the non-zero right-hand side. Okay, if we substitute the homogeneous solution into the left-hand side, it gives us 0. All right, so that doesn't contribute at all to the right-hand side. But one thing to observe is even in the case of, actually just specifically in the case of constant coefficients, right, we've seen how to solve the case of constant coefficients, right, where A and B are both constant, right? If we, say, substitute in a polynomial for y, if we substitute a polynomial in here, we can work out its first derivative, its second derivative. That's quite easy. But it turns out what comes out from the left-hand side is a polynomial, generally of the same degree. So there's one observation we can make. Right? So we end up with a non-trivial right-hand side, which is a polynomial. Okay? What about, say, if we substitute in an exponential function into the left-hand side? Well, if it's an exponential function that's part of the homogeneous solution, we'll just get 0. All right, so that's trivial. But if it's an exponential function that's not, that does not occur in the homogeneous solution, right? We know if we substitute in an exponential function into the left-hand side, because we've got the first derivative, the second derivative, we're just going to end up with some linear combination of that exponential function back again, right? So in other words, if you substitute in an exponential function to the left-hand side, you end up with an exponential function, unless it occurs in the homogeneous solution. Similarly, with cosine and sine functions, you plug in a cos or a sine function into the left-hand side, you end up with a linear combination of cos and sine. right? It doesn't always vanish. In some cases it will, but not always. In general, you'll end up with a linear combination of cos and sine. And so on. So we can make these observations about the second-order linear equations with constant coefficients. We can make these types of observations and saying, well, if we put in a polynomial, we're going to get out a polynomial of the same degree back again. So what we can do is turn that observation on its head and say, if the right-hand side is a polynomial, all right, if we're dealing with just constant coefficients here, if the right-hand side is a polynomial, that means we'll make a guess that the particular solution, that is the part of the general solution which contributes to that non-zero right-hand side, we'll make a guess that the particular solution is also a polynomial of the same degree with some coefficient, right? What if we see the right-hand side is an exponential of some form, right? If it's an exponential, then what we would do is, based on the discussion we've just had, based on the observation I've just made, if it's an exponential on the right-hand side, we'll turn that observation on its head and say, well, let's make a guess that the particular solution is of the same form, because we know it's only that particular solution that contributes to the non-zero right-hand side. Okay? And so on for certain other types of functions. In fact, there's a table here that summarizes this discussion. In fact, I guess we refer to this table on the next page, but I'll just quickly describe what I've got here. So you can think of this as there being four distinct entries in this table. So the column labelled R is meaning the form of the right-hand side. Okay, I mean so here in this first entry we're saying if the right-hand side is of the form of an exponential, then this next column, the G, so it's R for right-hand side and G for guess, right? The corresponding guess for the particular solution would be that the particular solution is an exponential function of the same form, right? If the right-hand side is a polynomial of degree n, we would guess that the particular solution is also a polynomial of degree n. And so on. There are two more entries here. So if there's either a cosine or a sine function on the right-hand side, then we would make a guess that the particular solution is some linear combination of cos and sine functions. Okay, and similarly with products of exponentials and cosines and exponentials and sines, and I think you could even include polynomials in there. But this is just a summary. So I'll refer you again to the Stewart textbook on pages 1173 to 1177, and it's actually on this page, I think, that there's a nice summary of all these results. But this all comes from that observation I was talking about earlier, right? It all comes from that observation that if we have an equation with constant coefficients, and remember this method of undetermined coefficients actually is we're only going to be working with that special case where we have constant coefficients. Okay, we know we can solve the homogeneous equation or the homogeneous part of the general solution if we've got constant coefficients here. So this is just based, or this result is based on that observation, right? If we plug in a polynomial to the left-hand side, or if we plug in a polynomial to this expression on the left-hand side, out comes a polynomial. All right, if we plug in an exponential, out comes an exponential, and so on and so forth. Guys, there are plenty of seats down here. I'm not supposed to have people standing in a lecture. Thanks. All right, so I'll actually make use of this table. In this outline of the method. So it turns out it's not always as easy as I've made out here, although this does provide the foundation for the method. Okay, so on page 24, I just provide the steps that we work through in order to apply this method, so-called method of undetermined coefficients. And I'll work through some examples just to, show you the basic principle, but also show you how some complications can arise and how we can deal with that. So let's just have a read of the rules or the basic steps involved in this procedure. So step one is just to find the general solution to the homogeneous equation. So the way I've worded it there, find a solution YH, I actually mean find the general solution YH to the corresponding homogeneous equation. Okay, so that's the first thing we do. We work out the YH part of the general solution. So remember, that's just referring to this statement on page 23, that the general solution of a linear, non-homogeneous differential equation is always of this form. In fact, in the exam, if you get stuck in working through this, you can be certain that if you write this statement, general solution y equals YH plus YP, there'll be 1 mark in that out of a possible 10. Okay? All right, so that's the first thing we do in this method. All right, the second thing we do is have a look at the right-hand side. Have a look at the function on the right-hand side. Generally, it could be a sum of terms. So here I've just written R1, R2 up to Rn, for example. And what we can do is make a guess based on the discussion we've just had, based on this the result that's summarised in this table on the previous page. We can make a guess for the particular solution, or at least for terms in the particular solution that correspond to each of these terms on the right-hand side. So we look at the right-hand side. We look at the first term, R1. It's a polynomial. So our guess for that term would be a polynomial of the same degree. All right. We look at R2. It might be an exponential function. Okay. Then our guess for the particular solution that gives rise to that exponential term would be an exponential term itself, and so on. All right. So that's steps 1 and 2, the basic procedure. However, things can go wrong, and life's not always easy, right? But here, things can go wrong. But we can categorize what can go wrong. Right? We can keep track of every possible thing that can go wrong. So this is great, right? Step 3, let's have a look at what it says here. If a term in our guess appears in the homogeneous solution, we can replace that guess by another guess where we just multiply the original guess through by x. Okay? Step 4, if that still doesn't work, right, if the x times our first guess is still in the homogeneous solution, that can happen, and I'll show you an example where it does happen. Well, we have to modify our guess again and just keep multiplying through by x. So instead we'd make a guess of x squared times g of x, and so on. All right, so these steps 3 and 4 are just telling us that in some cases we may need to modify the guess. All right, now that seems very straightforward, what I've said there. We make a guess, no, it's in the homogeneous solution, multiply by x, and now it should be okay. Now, if that's still in the homogeneous solution, multiply by x again, and just keep doing that until we find something that is not in the homogeneous solution, and this works. Why does it work, though? Well, the proof of these statements, the proof uses this method, reduction of order, that I've just been talking about. The proof uses reduction of order. So really what that means is we make a guess based on these observations. We make a guess, and it's like, oh, unfortunately that guess already appears in the homogeneous solution. So that means if I substitute the guess back into the left-hand side, I'm going to get 0. I'm not going to be able to get any information whatsoever from that guess. So this is telling me we have to modify that. But what we could do is take that original guess, multiply by some function of x, say multiplied by u, substitute that into the differential equation, and if our original guess solves the homogeneous equation, it means we're going to be able to get some information about this function u. Right? And it turns out, in this case, that function u always works out to be a linear function of x. And so that's where this x comes from. Similarly for x squared, right? You just keep repeating this process using reduction of order. So it's a reasonably straightforward calculation. Okay, so what do we do with these guesses, though? Well, the very last step is we substitute the guess into the left-hand side of the differential equation, right? Have a look at the guess, or the guesses listed in this table. So if we have a right-hand side that's of this form, so k is some constant that's given, we make a guess, well, sorry, I should say k and gamma are some constants that are given. So this number up in the exponent is the gamma, Greek letter gamma. This guess is still an exponential of the same form, e to the gamma x, but this a is some coefficient to be determined, right? It's an undetermined coefficient. So what we're going to do is, and this is what's outlined in step 5, we take our guess, we take our completed guess, substitute it into the left-hand side with all these undetermined coefficients, and then match up coefficients at the end. So actually this exercise reduces to just a matter of solving some algebraic equations. In fact, everything we've seen so far, these first-order differential equations, the separable ones, the linear ones, and so on, everything we've seen so far for solving these general types of differential equations involves some form of integration. Integration is a very useful skill for solving differential equations. But it turns out, for these equations with constant coefficients and where the right-hand side is of a particular form, we don't have to integrate anything. All right? We just end up having to solve a few algebraic equations. Let's have a look at an example. So here we've got a second-order linear non-homogeneous equation with constant coefficients. And so I'll just scrape together one mark here and write the general solution is just yh plus yp. Make this observation. So there are 2 steps in working out the general solution. For yh, we have the characteristic equation is lambda squared. Remember, the second derivative always contributes a factor of lambda squared, the first derivative a factor of lambda, and the y itself just contributes a factor of 1 to the characteristic equation. All right, so we end up with lambda plus 2 all squared equals 0. So we end up with 1 value of lambda. Okay, so that implies that for the homogeneous solution, remember it's a second-order linear equation. Well, in this case, it's the homogeneous solution I'm working out. So I've worked out 1 value of lambda, so I know e to the negative 2x is a solution. But remember, this corresponds to that case in the table on page 22, that second case where we have just one root of the characteristic equation, and to get that second linearly independent solution, we just multiply the first one by x. Okay, so the yh in this case is just going to be a plus e to the negative 2x plus b x e to the negative 2x, where a and b are arbitrary coefficients. All right, so that's the first part done. What about for the particular solution? Well, in this method, we observe that the function on the right-hand side is a polynomial of degree 2. So for the guess, for the particular solution, we would guess that it is also a polynomial of degree 2. But I'm going to make the guess that it's the most general form of the most general polynomial of degree 2. So I'll write ax squared plus bx plus c, where a, b and c are these undetermined coefficients. All right. So now I'm going to substitute that into the left-hand side of the differential equation and then just match up the coefficients on both sides. And hopefully I'll have enough information that I'll be able to solve for a, b and c. Let's have a look at how it works out. Okay, so the first derivative is just 2ax plus b. And the second derivative just works out to be 2a. All right, so that implies that yp double dash plus 4yp dash plus 4yp equals, let's put it all together. So we have 2a for the second derivative plus 4 times the first derivative, which is 2ax plus b, plus 4 times yp itself, which is ax squared plus bx plus c. All right, I guess what I could do now is just write down all the constant terms, the linear terms, and the quadratic terms, all in one expression. So what are the constant terms we have? We've got 2a here plus 4b coming from there, plus 4c coming from here. We've got linear terms, so that's x multiplied by, so what have we got? We've got 8ax, and we've got 4bx, and we've got one quadratic term, which is just 4ax squared. All right, but this should be equal to the right-hand side. What was the right-hand side? 8x squared. So 8x squared. So now let's equate coefficients. So we equate coefficients. So the coefficients of the x squared, we just end up with 4a equals 8. All right, so that implies a equals 2. All right, the linear coefficient, the coefficient of x, here we have 8a plus 4b equals, well, really on the right-hand side we've got 0 times x, so that equals 0. We already know what a is. We already know a is 2, so that's just 16 plus 4b equals 0, so that implies b is negative 4. All right, and now for the constant term, or I guess if you like the coefficient of 1, we've got 2a plus 4b plus 4c also equals 0. All right, the coefficient of 1 is 0 on the right-hand side. We already know a and b, so we've got 4 minus 16 is negative 12, plus 4c equals 0, so that implies c equals 3. All right, so we've got enough information there to work out those coefficients. So that implies the general solution then is yh plus yp. I'll write it one more time. Do I get 2 marks in that case? No. So a e to the negative 2x plus bx e to the negative 2x plus, now here's the form of the particular solution that we started with. So that's 2x squared, minus 4x plus 3. And there's our general solution. All right, so that's just a stock standard example of how we can use the method of undetermined coefficients. We look at the right-hand side and make an educated guess for the particular solution. This is after working out the homogeneous solution. Yeah?
You said before that you don't know if that's always going to work, so how do you know if that's correct?
So where it won't work is if the guess occurs in the homogeneous solution. Let me show you what I mean. Here's one I prepared earlier. On page 25, for example. Okay, so actually one aspect to your question is this, right? It's an equation with constant coefficients. Okay, so I'm only talking about ODEs with constant coefficients. If there were coefficients involving x non-trivially, then this wouldn't necessarily hold. It'd be a completely different story, right? I'm only talking about constant coefficients here. All right, so let's have a look and see what can go wrong. All right, here's again a second-order linear non-homogeneous ODE with constant coefficients. I know the general solution is of the form YH plus YP. And at this stage, I'll just say check. So, I mean, you can go through the details of this calculation yourself. But for the homogeneous solution, just check that you end up with, in this case, 2 real values of lambda, and they would be -2 and 1. So the 2 linearly independent solutions of the homogeneous equation would just be e to the -2x and e to the x. So what about for yp? Right, using this method of undetermined coefficients. Where can it go wrong? So what we do is have a look at the right-hand side. It's -3 times this exponential. So that means we would guess, in the first instance, yp equals some coefficient a to be determined, multiplied by, well, what have we got on the right-hand side? We've got an e to the -2x. So I'm going to write e to the -2x in the guess here. Okay. Now, what I'd really like to be able to do is substitute that into the left-hand side of the equation and then match coefficients and solve for a. But can I do that? I think this comes back to the question that was asked before. Right? This e to the -2x occurs in the homogeneous solution. So what that means is if I substitute this into the left-hand side, it will vanish because it's a solution to that left-hand side equals 0. All right, so I'm going to get no information whatsoever about A. So that won't work. I'll put a question mark there. Will that work? Cross. No, it won't. Okay, maybe I'll just make a note. It won't work since e to the -2x is in YH. Okay, so we modify the guess. We modify the guess by just multiplying through by x. So our new guess will be a times x e to the -2x. Will this work? And well, the method of undetermined coefficients says yes, it will. This does not occur in the homogeneous part of the solution, and it's not in YH, so it's okay. And in this case, just check that yp works out to be x e to the -2x. So in other words, a works out to be 1. I won't go through the calculation. Just here in the last few minutes of the lecture, I just want to show you what can go wrong. Okay? Sometimes we need to modify our guess a few times, well, twice. So again, just check that the homogeneous solution in this case is a e to the x plus bx e to the x. All right, so what about yp? I wonder if you can see what's going to go wrong here. So our first guess. Yp equals some coefficient times e to the x, because I look at the right-hand side. It's an exponential. I'm going to guess it's an exponential as well. Will that work? No, it won't, right? That's not going to work because e to the x occurs in the homogeneous solution. All right, so modify our guess. Multiply through by x. Will that work? Once again, no it won't, because x times e to the x is a solution of the homogeneous equation. So we just keep modifying. And like I said, this is all proved using reduction of order. And it turns out that one will work. And just check that a equals 1/2. Okay, so we end up with a particular solution that way. All right, just one more example. This is just a slight variation on the example on page 26. So everything is the same as the previous example, but now we've got this additional term, this additional x. Okay, so in this case, what I'm referring to is the particular solution is the sum of two particular solutions where, say, yp2 would contribute to the x and yp1 contributes to the exponential. Okay? So we've already worked out yp1 from the previous page. So I'll say see page 26. For yp2, though, we would guess yp2. Well, it's just a polynomial of degree 1, so we would just guess ax plus b and work through the details that way. Okay? So I should stop there. That's the method of undetermined coefficients, one particular method of solving non-homogeneous equations. Just while you're packing up, I'll just show you some nice, lovely diagrams of these solutions to that very last equation. And look, one interesting thing, if we zoom out, we're no longer able to detect some of the behaviour of the solution. Just one little observation. The scale of the solution is sometimes important. All right, anyway, cheers, guys.